Now that we've covered section A, let's look at an example of section B. And again, I'll repeat that the solutions are available on the Keats page, so I'm not going to go through every one. Also, the main point here, as it says in bold at the top, is that you should answer only one of these questions. So have a look at the beginning of the exam and decide on one. So I'm not going to do two. I'm going to choose three. And for the sake of time, so you don't have to watch a very long video, I'm only going to do parts A, B, and C. Now I partly chose 3A and B and C because when I first wrote this practice exam, the only questions I wasn't quite sure about what I was asking happened to be these ones, and the version I first posted wasn't very clear. This should be much more clear. And as I said on the email I sent around, the benefit of the actual exam is that it's got several other lecturers who have to approve the exam, so these type of mistakes don't creep in. But anyways, let's look at 3A. So it's asking inside of a star, which in this case is the sun. So it's got a radius of 1 solar radius and a luminosity of 1 solar luminosity. When you're inside at a radius of 0.9, there's a temperature of 1,000,000 Kelvin. And at the surface, it drops to a much lower value. The temperature does of about 5,800 Kelvin. So the question is, consider that at some location R, there is a black body flux. Now we have to think about what that means and compare this to the flux that's due to the internal power source F, and then calculate the ratio of these at that position R. So what would the black body flux be? What we mean there is that we saw when you have an ideal gas that's at a certain temperature and it acts as a black body, we know that this flux is equal to sigma times T to the 4th power, the Stefan-Boltzmann law, and that's what we're talking about. Now the flux that flows through, we know originates in the core and is due to nuclear fusion, but those details aren't actually necessary. All that we need to think about is that at the upper layers, we are not creating this. It's just flowing outwards. All right, so let's look at how we'd answer this. So I've got my work that I've written out, and I've got a new page. So this is for question 3A. And let's first of all, just as I mentioned, we have this power that's produced in the core and then flows outwards. And so at an outward position, we know that the luminosity, that power, has to be the same at these different radial positions as long as you're outside of the core of the star. So what I mean is that at a position of 0.9 solar radius, which is little r, it's the same luminosity as it is at the surface. And then I also mentioned that we can think about both the Stefan-Boltzmann law, but we can also just think about the definition that a flux is this power or energy per second per element of the surface area. So we can multiply the surface area at that radius, which is 4 pi r squared, times this flux. And since we said that that has to equal, sorry, this is equal, that's an equal sign there. So this luminosity then is also equal to at the surface. So then that's equal to 4 pi r squared, where now r is at the surface, and this is the flux at the surface. Okay, that's fine. But where the Stefan-Boltzmann law comes in, and we can put this, so what we're given is actually we're given at the surface, we were given its temperature, and in that case then we have that this flux flowing outward that originates from the core. The Stefan-Boltzmann law then is sigma times T to the fourth, where this is the surface temperature. Okay, now we can solve for that flux at the radial position R using those two formulas. And we get that this is the ratio of the surface radius squared over R squared times, basically times that Stefan-Boltzmann law. Okay. Now, what was that black body flux? What is this thing that I'm calling FBB? Well, this is basically the flux that you get from the Stefan-Boltzmann law when you're thinking about this at that position due to the temperature at that position inside. And on the surface, it's kind of apparent that we are measuring the flux flowing outwards, and we can't actually see the flux interior. So this flux is hidden from us, but it's due to that temperature at that position. So this is sigma TR to the fourth power. And now we can take the ratios. So we have F of R over the black body flux at that same R position. And we just substitute in here that we had the surface radius squared over R squared. And now this is a ratio of temperatures as well, where we have Ts to the fourth over the temperature at position R to the fourth power. And we can now plug in those values. So we have 1 solar radius over 0.9 solar radius squared times 5,800 Kelvin over a million Kelvin to the fourth power. And that should give you a small number, which is 1.7 times 10 to the minus 9. And that's unitless, right? We can see that because the solar radius canceled and kelvins cancels. All right, so that's part A. Part B is saying, well, let's see, what is it asking? Let's get a reminder. It's saying explain the simplifying assumptions which the assumption that's validated by your result from part A. Well, what do we see from part A? We see that if that ratio is very small, that means that this flux that's flowing through is actually much smaller than what you would get if you were just measuring the flux based on the temperature at that location. So in other words, this black body flux is much higher. And so what that's telling us then is that this dominant isotropic blackbody flux we think about is coming from thermoequilibrium. So we have that those two assumptions should indeed be valid. So I can write all this down, and I can do it in my bad handwriting. Hopefully you guys have better handwriting. It'll make my job a lot easier when I'm marking. I'll just do it as fast as I can. Luckily, you don't have to be super fast because you have the benefit of more time for your exam. So we'll put the result from part A. Shows that the flux that from the layers coming outwards, the flux flowing through is only a very small fraction compared to the isotropic. Well, let's just say compared to the black body flux. Thus, an assumption of isotropic black body radiation from we could say in thermodynamic equilibrium is valid. Okay, now finally we have part C. And what is part C asking? It's saying, calculate the average time in years for photons from that radius of 0.9 solar radius to diffuse to the surface if the average opacity in that region is 1,000 meters squared per kilogram and the density is 1 kilogram per meter cubed. Now, this is a relatively easy question, particularly as you have full access to look up the equations for opacity, and also then we can think about, we're asking for an average time, and we're really just then thinking about how do the photons travel through this material, and we had studied the diffusion timescale, the fact that they actually travel very short distances on the order of centimeters before they bounce around and are scattered. And we call that scattering a diffusion. So we're looking at the diffusion timescale. So we can write down a couple of equations. And as I said before, giving in words what the equation is helpful. And I highly recommend it. So for example, we'll write out that this is the diffusion timescale. Again, try to have better handwriting than I do. So I'm not setting a good example here, but hopefully you can do better. So this is the diffusion timescale, was some distance that you're considering squared over LC. Now, what is L? L is the mean free path. So we know the distance, but we do not know the mean free path. However, we have a formula for that. Which is L is 1 over n sigma, and n is the number density, sigma is a cross section. Now, we don't know either of those, but what are we given? We are given a mass density, and we are given an opacity. So opacity kappa is related to these quantities. So we can look up what kappa is. And so let me do that. Whoa, if I can get back to my, don't know what I've done here. Okay, let's keep going. So the opacity kappa is n sigma over rho. Now that's good because we don't know n sigma, but we do know kappa and we know rho. So what we can do is then write the mean free path in terms of things we know. Or in other words, let's substitute in that n sigma is now 1 over L. So this means we've got 1 over L times rho. And now solving for the thing we want, which is L, we've got that is 1 over kappa rho. Okay? And we can insert that into our diffusion timescale. So this now is going to be, since we're dividing by L, the kappa and the rho go on top in the numerator. So kappa rho d squared over c. And now we know all of those things. I've given you examples of plugging in numbers and showing your units, so I am not going to do that. And I'm going to end our revision lecture.